So our lesson today is on logarithmic and exponential functions. And we'll take a look at an article excerpt from David Parrish and some of his research. It looks like exponential growth is the aim of businesses worldwide. So the most powerful of all of these businesses referenced earlier in the article, the models, is an exponential growth business model. The most successful business in the digital industries have a scalable business model that allows them to grow exponentially. Unlike linear growth, which increases steadily, exponential growth is about rapid growth. For example, a doubling in size every 6 months. So on a graph, linear growth is a straight line we are familiar with, whereas exponential growth curves upward. So you would see a curve. So here's a stunning example between Hyatt Hotels and Airbnb. The hotels corporation Hyatt has 600 hotels worldwide across 10 brands, and this means they have 15,000 rooms available globally, and they have 95,000 employees. At the time of this writing of the article, the corporation was worth $8.07 billion. So in contrast, Airbnb, so it's a website for people to list and find rent lodging. It has over 1,500,000 listings in 34,000 cities in 190 countries. And so the company has less than 2,000 employees. Contrast that with the 95,000 for Hyatt. And at the time of this writing, the company was worth $13 billion. So furthermore, growth at Hyatt will be relatively slow, expensive, and linear. So going up in a linear fashion, which is still positive growth. And its companies based on bricks. In contrast, growth at Airbnb will be rapid, inexpensive, and exponential. Exponential growth. Its company based on clicks. So there's your real life example to get us started. We'll take a look at an example also by Facebook. Facebook is another company that is known to have exponential growth. And let's imagine that on day 1, we had 10 users. And each of those 10 users told 10 users. So on day 2, we had 10 squared users. And now each one of those told 10 users. So we would have on day 3, we would have 10 cubed users. And so on. Day 4, we would have 10 to the 4th users. So we could represent this function by saying on day X, we could expect to find 10 to the X users. So we could go over here and graph this. So on day 1, we had 10 users somewhere way down here close to 0 on the y-axis, followed by 10 squared, which is 100, so up just a little bit. And then on day 3, let's go back here and write these out. We have 1,000, so day 3 we're up to 1,000. Add another 0 on there, so we're up to 10,000 users on day 4. Day 4, and we have to go all the way up to 10,000, way up here at the top. And so you can see this curve that's happening. It raises rapidly, and that is a good sign, a good model for business growth. Let's take a look at the definition here for exponential growth. So there's exponential behavior. So there's actually 2 types of exponential behavior. We can have growth, but we can also have decay. So exponential growth is the value of x, as the value of x increases, the value of y increases. So this is your exponential growth function. Versus exponential decay. So as the value of x increases, so you can see x increases as we go to the right, but the y value gets smaller. The y value decreases. So this is an important definition to remember. So Another new term is asymptote. The word asymptote is just referencing a line that a graph approaches as x or y increases in absolute value. So as you can see, this graph approaches the x-axis. So the x-axis is the asymptote. And you can see also as this function gets smaller, over here the x-axis is an asymptote here as well. So in general, for the function y equals ab to the x, these are key points to remember. If a is greater than 0, right, this value right here, if this value is greater than 0 and the b value is also greater than 1, the function represents exponential growth, right? So if we have greater than 0, so we could have y equals 2 times something greater than 1, so let's say 4 raised to the x power. That would be an example of exponential growth. We could even have y equals 1/2 times some number greater than 1. See, this is still a number greater than 0 raised to the x power. Both represent exponential growth. Versus for exponential decay, we would have a greater than 0 as well. However, b is a fraction. B would be between 0 and 1. Notice b is never negative. So we could have y equals 2 times 1/3 to the x power. That would be something representing exponential decay. In either case, the y-intercept, 0, a. So you can see here the y-intercept happens at this a value, so it would be 0, 2 if we were representing this exponential decay function. Now, here are a few examples. It says determine the function represents exponential growth or decay. So we can look at, okay, these values have to be greater than 1, or sorry, greater than 0, which in each case they are, which is what we need for both exponential growth and decay. And then also check if b is greater than 1 or between 0 and 1. So here it looks like our b value, so this is our a value, this is our b value, b is between 0 and 1, so that means this must be exponential decay with a y-intercept of 0, 12. So if we were to make a little graph of that, 0, 12, we would see something like this, decay. Part B, we have 2, so that's a number greater than 1 right here. B value is greater than 1, so we have exponential growth with the y-intercept of 0. Here's our a. This is our a. This is our b. A is for our y-intercept. B is for our determining if it's growth or decay. So 0.25. So on this, we could draw a quick sketch, and we would have 0.25, and we would see something like this: exponential growth. And then for y equals 6 to the x, notice there is no a value, so a would equal 1. Also, our b value is 6, meaning it's greater than 1, so we have growth. And we could expect to see, we didn't label, sorry, 0, 1 would be our y-intercept here, and its growth. Just a very rugged sketch, but something that demonstrates we understand what the graph of growth versus decay looks like. And for part D, I'd like you to try that one on your own.